In this lesson, we're going to talk about extrema of a graph of a function, which is talking about the maximums and minimums. And there are two types of extremas. We have relative and absolute. So let's just consider this graph that I've drawn here. We have a lot of curves and valleys and peaks. And we say that something is a relative maximum if it's the maximum for the stuff that's near that point. And so for a relative maximum, we're kind of putting on those horse blinders and just looking in a region. And so our relative maximum that we would have would be the point -4,3, the point 1/2, 2, and the point 5, -3/2. Those would be considered relative maximum. And for the same idea, we'd have relative minimum at the point -2, -2, and the point 4, -3. I find it's important when you are talking about the extrema to list the point, give us both the x and the y value, because that gives us the most information. Where does it occur? That's the x value. And what is its value? That's the y coordinate of the point. And so this relative extrema occurs at x equals 4, and its value is -3. So here are the three definitions that you can find in our text for relative maximum, relative minimum. And then we have absolute maximum and absolute minimum. The absolute means we're looking at the big picture. And so for us, the absolute maximum is going to be this point right here, absolute. I put a rectangle around it. And the absolute minimum is going to be this one, 4, -3. So let's look at another example. Relative extrema only occur at a critical point. Remember that a critical point is the place where the derivative either equals 0 or the derivative is undefined. So if we were to consider the function f at x equals x squared minus x minus 12, and we're going to put this on a closed interval, and let's put it on the closed interval from -3 to 5. So we're looking only from x values -3 to 5. To find critical points, we would take the derivative, and the derivative of our function is 2x minus 1, and the derivative equals 0 when x equals 1/2. We also know that the derivative is undefined at the endpoints of our domain, so at -3 and at 5. If I were to stick a little tangent line here, remember a tangent line is supposed to just touch the graph in one point. Well, I could pivot it in many different directions, and so we wouldn't say that the derivative exists at x equals -3. So our critical points are x equals -3, 1/2, and 5. So now, looking at our graph, so here I drew the graph, we can see that a relative minimum occurs at the point 1/2, -12 1/4. We see that relative maxima occur at -3, 0 and at 5, 8. And the point 5, 8 would be our absolute max, and our absolute min would be the point 1/2, -12 1/4. Okay, so we're going to do two examples now that we're going to walk through the points of finding the derivative and using the first derivative test to find out where something is increasing and decreasing. Notice that between a relative max and a relative min, the graph is decreasing. Between a relative min and a relative max, the graph is increasing over that whole interval. So we're going to look for the extrema of the function f at x equals x cubed plus 6x squared minus 15x plus 2. We are going to also restrict ourselves to a closed interval from negative 6 to 6. Okay, so the derivative of our function is going to be 3x squared plus 12x minus 15. And I had mentioned in a previous video that factoring can make our life easier. Yes, we can find out where the derivative equals 0 using the quadratic formula, but factoring is really nice. So if I factor the derivative, I end up with the f prime of x equals 3 times x plus 5 times x minus 1. I set that equal to 0, and we find that the derivative is 0 at negative 5 and 1, and so those are critical points. We also have critical points of x equals negative 6 and x equals 6 because those are the end points of our domain. And so now we're going to do the first derivative test. If I plug in a number between negative 6 and negative 5, and I'm actually going to plug in negative 6. That's maybe bad form, but if I plug in negative 6, I end up with 3. Negative 6 plus 5 is a negative number. Negative 6 minus 1 is a negative number. So we have a positive times a negative, and we end up with a positive function. So we're increasing between negative 6 and negative 5. If I plug in a number between negative 5 and 1, like 0, we end up with positive times negative. So the first derivative is negative on the interval from negative 5 to 1. So that means we're decreasing. And then if I plug in a number bigger than 1 but less than 6, I'll plug in 4. If I plug in 4, I end up with a positive times a positive times a positive, which means this derivative is positive, and we're increasing again. So thinking about what happens, we are increasing, decreasing, increasing. So that means we start at a low point. So a relative minimum occurs when x is negative 6. A relative max occurs when x is negative 5. Going down, a relative minimum occurs when x is 1. And then going to our last endpoint, it's increasing in this interval. So we have a relative max when x equals 6. And if I check out what those numbers are, I like to look at them as points. We say the relative max are at negative 5, 102. I plugged this into the original function. We're wanting to know where the original function is biggest. And then 6, 344. Our relative minimum occur at negative 6, 92, and 1, negative 6 as points. And so for the absolute maximum, we'd look for the biggest y value, and that happens at 6, 34. And for the absolute minimum, we'd look for the smallest y value, and that happens at 1, negative 6. So our absolute min is 1, negative 6. And let's do one more example. We're going to let our function g at x equal x to the 1/3, or the cube root of x. And we're going to look at the closed interval from negative 8 to 8. When I take the derivative of g at x, I get 1/3 x to the negative 2/3. A negative exponent means we're going to bring this x to the 2/3 down to the denominator. So we just have 1 divided by 3x to the 2/3. When does the derivative equal 0? Well, the fraction 1 over 3x to the 2/3 equals 0 has no solution because 1 equals 0 never happens. So we have no solution. G prime of x is undefined when the denominator equals 0. So if we are solving 3x to the 2/3 equals 0, we actually end up with x equals 0. So the derivative is undefined at x equals 0. And our critical points are negative 8, 0, and 8. Remember, the end points of a domain automatically are critical points. Okay, so I have 3 critical points, and we're going to do our first derivative test, negative 8 to 0. If I plug in a number like negative 1, G prime at -1 actually equals 1/3, which is a positive number, which means we're increasing from -8 to 0. If I plug in a number between 0 and 8, like +1, G prime at 1 equals 1/3, which is a positive number. So we're increasing from 0 to +8. And that means we do not have a relative extrema happening when x equals 0, because it's increasing to the left of 0, and then it continues to increase once we passed 0. And so there is no relative extrema here. They only occur at the left and the right. While if my function is only increasing from left to right, my relative minimum would also be the absolute minimum, and that is at the point -8, -2. And then if we're only increasing, the biggest the function occurs is at the right-hand side when x equals 8, and that's the point 8, 2. So if you wanted to graph this function, just to know what it looks like, it's only increasing from left to right. So here's my absolute minimum, and here's my absolute maximum.